Welcome back, everyone. So far, we have learned how to set up the equation of motion of a multi-degree of freedom system, and we also saw that a multi-degree of freedom system is represented by different modes. So the total response is actually contribution of the response of each mode. In today's class, what we are going to learn is basically how to get the response of a multi-degree of freedom system in terms of response at each degrees of freedom. So we are talking about basically displacement response, and we'll extend the same concept to find out other type of response quantities like shear forces and moment. And we are going to see for both type of system, undamped and damped system, how to actually get the expression for the displacement response. Okay, so let us get started. In the last class, we discussed basically the frequency and the mode shapes, okay, of a multi-degree of freedom system. Okay, so we had frequencies and mode shapes. Okay, and we said that if a multi-degree of freedom system is excited through some excitation in general, the response of each degree of freedom would not be harmonic, but there exist few characteristic shapes in which if they are provided displacement according to those shapes, then the multi-degree of freedom system would have harmonic response at each degree of freedom, and it is going to maintain its shape throughout the vibration, and those characteristic shapes are actually called mode shapes. And because the response is harmonic, each of these modes would have their own frequencies, which is basically the time taken to complete one cycle of motion. Okay, that is the time period, and we can get frequency, okay, using the relationship as 2 pi by time period. So we discussed that, and we said that the total response of a system, okay, would be contributed by each of these mode. Okay, and let us say if the mode shapes are represented through this vector phi1 and phi2 and so on. Okay, then we said that the total response would be combination of each the contribution due to each of these mode shapes. Okay, and depending upon how much of those contribution are, some modes are going to govern the response, and we are going to learn about that later. But right now, let us consider that the total response, which is nothing but the response at each degree of freedom, let us say, and so on. Okay, it can be written as okay, response due to all mode shapes, which are represented through this shape vectors. Okay, and so on. Now, we already know the frequency, we already know the mode shape. So the problem statement here is, given the vector u, is it possible to find out the factors that need to be multiplied to these mode shapes so that we can get the modal decomposition or modal expansion, we call it, okay, of this displacement vector here. So basically our objective here is to find out these factors here, because once we derive expression to find out these factors, then we can find out the total response as a linear combination of contribution due to different mode shapes. Okay, so let us see how do we do that. So this is basically called, this what we have written here is modal expansion. Okay, modal expansion of displacements. This is called modal expansion of the displacement. And let us look at that, how to get those factors. So let us assume that the vector u is basically, okay, so I'm just going to write these expression that we had written here in terms of summation. So let us say we have n modes here, n degrees of freedom. Okay, so we'll have phi, which is the mode shape here, times qr. Okay, and this qr is basically these factors that I'm talking about. So our goal is to find out those qrs. Now we can write the same summation in terms of multiplication of modal matrix times a vector q as well. Okay, where vector q contains all these factors as column vector. Okay, so these are called modal coordinates. Okay, the vector q is basically q1, q2, and so on, and these are called modal coordinates. Okay, and these are the factors that are required to find out the total response, okay, by combining different modes here. Okay, so let us see how we can find out these individual QR here. Okay, now we are going to utilize again the condition of orthogonality of the modes, which basically says that if I have two different modes, okay, then if I take the product with respect to the mass matrix, okay, the product of the transpose of one mode times the mass matrix times the product of another mode, that would be equal to 0, okay, as long as those are different mode shapes. Okay, so what I'm going to do here, I'm going to pre-multiply this expression that we have written, okay, with phi n to the power t times the mass matrix. So we get here as well, on the right hand side inside the summation, I will have phi n t times m. Okay, remember this is phi r here, okay, not 1. This is phi r times qr. Now as we know, due to modal orthogonality, when I expand this summation, okay, when I execute this summation, what will happen? Most of the term will vanish except when r is equal to n. R is equal to n. That is the only term that is going to survive. Okay, so knowing that, the expression that I will get is actually phi n t times m, and now I will substitute r equal to n. Okay, this is n and this is qn here. Okay, so qn, the modal coordinate, I can write it as phi n to the power t times m times u, and this divided by this expression here. Now if you look at the denominator, this is nothing but the diagonal element of the diagonalized mass matrix. Okay, so basically what I'm saying here, this is nothing but, in the denominator I can write this as mn, which is the nth diagonal element of the diagonalized mass matrix. Okay, so we have found out qn now. So we can do that for all the mode shapes and find out these factors, multiplicative factors for all the mode shapes. And once we know that, then we can combine modes using those factors. Okay, this would be more clear after we do one example. Okay, so let us take an example that we have been doing till now. So basically I have, okay, the same two-story representation of a building in which this here is 2k, this is k, this is 2m, and this is m. Okay, now we know that the mode shapes for, we had derived the mode shapes and we had got that, but this is degree of freedom 1 and this is 2. So this was half and 1. We had normalized with respect to the top story or u2. So my phi 2 here is -1 and 1. Okay, now the question is that at any time instant, let us say, okay, u of t at any time instant. Well, let us say u is given as 1 1, and what I have to find out basically the modal expansion of the displacement vector. So I have to find out the expansion of this in terms of some factor times the first mode shape plus some factor times the second mode shape. So basically I have to find out those factors q equal to q1 and q2. Okay, so let us see how do we do that. All right, so my q1 will be nothing but, okay, transpose of phi 1, which, so let me just first write down anyway. This would be phi 1 times u here. Okay, this would be phi 1, sorry, phi 1 transpose here, phi 1 transpose times phi 1. Now if you look at this, let us substitute those vectors here. So this is half 1, and the mass matrix is of course 2m 0 0 m, and here is the displacement vector for which we are doing the modal expansion. So this is 1 and 1 here, and in the denominator basically I have half 1 and then 2m 0 0 m times 1 1. Okay, so this I get as 4 by 3. Similarly q2 I can find out as by substituting phi 2. Okay, so this will be phi 2 transpose m u phi 2 m phi 2. The value that you get is basically you would be going to get q2 as minus 1 by 3. Okay, so you got this factors. Let us see whether we get the same expression or not. So basically my u1 or the basically the u vector, the displacement vector is 1 and 1. Okay, so let us use the 4 by 3 times the first mode shape, which is 1 by 2 and 1, and then have minus 1 by 3 the q2 here, which is minus 1 and 1. Okay, so if you look at here, get this as 2 by 3 plus 1 by 3, okay, plus 4 by 3 minus 1 by 3. So this we get as 1 1. Okay, so that expansion is actually correct. And if we want to represent this in terms of or like using some schematic in terms of the mode shape, problem is that, or the problem statement is, initially it is given displacement which is 1 at each degree of freedom. So you need displacement at both positions. So this is 1 here and this is 1 here. Okay, now this is equal to, you look at the first mode. Okay, the mode shape is, okay, so this is basically 2 by 3 and 1 by 3. Sorry, 2 by 3 and 4 by 3. So I can just write it like this. Okay, this is 4 by 3 and this is 2 by 3 here, plus sum of the second terms, which is plus 1 by 3 and minus 1 by 3. So let me again draw this here. Okay, and the second degree of freedom, something like this here, and then this. Okay, so this is minus 1 by 3, this is 1 by 3 here. Okay, so this is what we get. Okay, so this is nothing but 4 by 3 times phi 1 here, and this is minus 1 by 3 phi 2. Okay, so the total response, which is basically u, is represented like this. So you can see that through the modal expansion, okay, at any time instant, whatever the displacement is given can be expanded in terms of contribution of the first mode and the second mode and so on. If it has n modes, then there would be n such mode shapes. Okay, and vice versa, it can be also true. So the idea is that if we have n number of modes, they can be combined using these factors q1, q2, and so on to find out the total displacement at all degrees of freedom. Okay, and we are going to see how we are going to get these vectors. Now remember, this q that we have obtained here, it is at any time instant. Okay, but in general, q is a function of time. Okay, so this is for any time, fixed time instant t equal to, let us say, t naught. But in general, q is basically the function of time, which is the time variation. Okay, so at any time it would be distributed or contributed by different nodes. So let us get into that. So now what we are going to do here, actually going to solve the equation for free vibration response. Okay, so remember that our equation of motion is m times u plus k times u is equal to 0. Okay, we have said that my now we are going to write in terms of as a function of time t. Okay, so this is nothing but r equal to 1, and then the linear combination of linear sum of all the mode shapes. So it would be, let us say, phi r times, or let me just write in terms of n here. Okay, so let us say n equal to 1 to n. This is phi n times qn here. Now it is a function of t. So we need to find out this qn of t. Okay, and we have previously said that because each mode shapes respond as they respond in a harmonic fashion, so the displacement q and t, which is the generalized displacement or the time variation of that mode shape, can be written as an cos omega nt plus bn sin omega nt. Okay, where this an and bn are basically constants that need to be found out using initial condition. If this is our equation of motion, the initial conditions are typically given at displacement vector at time t equal to 0 and the velocity vector at time equal to 0. And utilizing this, we find out a and bn. Okay, and omega n is basically the frequency, the circular frequency of the nth mode. Okay, so let us see how do we get the constant a and bn, because once we get that, then we can find out the overall displacement vector. Okay, if you utilize the initial condition, okay, we have the expression for u here. Let us get the, so let me just rewrite it. Okay, this is nothing but summation of phi n, which is the mode shape, times q and t, which is a n cos omega nt plus b n sin omega nt. Okay, and we can similarly get the velocity by differentiating with respect to time. The same expression here, this would be omega n phi n, and here it would be minus a n sin omega nt plus bn cos omega nt. Okay, so let us substitute t equal to 0 to get these expressions here. So that would give us u0 as summation n equal to 1 to n phi n times an, and then summation, sorry, the vector velocity vector u dot 0 as summation n equal to 2n omega n times phi n times bn. Okay, so this is the expression to that we would utilize to find out the constants an and bn. Now, if you look at an and bn, and let us say my qt is written as this expression here. Okay, an cos omega nt. So this is the expression, that the general expression, right? Solution that we had assumed, sin omega nt. Now, if we say that, let us assume an equal to q, oh sorry, not qt, q dot 0, q0, and bn omega n equal to q dot 0. Okay, then I can write this expression as q0 cos omega nt plus q dot 0 divided by omega n sin omega nt. Remember, these are also constants here, but why I'm writing it like this, so that my qt is similar to the expression that we had obtained for single degree of freedom system in terms of u0 and u dot 0, but now we obtain here in terms of the modal coordinate. Okay, so I'm just making this substitution here so that it is, we can correlate it to single degree of freedom system. So if that is there, then this expression can be written as n equal to this phi n times q0, and this expression as phi n times omega n q dot, sorry, no omega n here, just q dot 0. Okay, now we can look at these two expressions, and q0 and q dot 0 are nothing but, you know, the expressions similar to what we had derived here. Okay, so we can utilize the same expression to find out the value of q0 and q dot 0. Okay, so basically, so then remember, this is qn0 for nth mode. Okay, so just be careful with that, all things we are doing for the nth mode. This is again qn here, qn, qn here. Okay, so my qn of 0 becomes phi n t times mass, and this vector is basically u0 now, and again in the denominator I have mn of, and q dot 0 is phi n of t mass q dot 0, then mn is here. Okay. So utilizing these two expressions, we can get qn0 and q dot n0, and once we have that, then the expression for qnt is known. Okay, sin omega nt, and once qnt is known, then we can do that for each and every mode, and we can find out the total response using this summation that we had derived. Okay, so this is basically n equal to 1 to n phi n times qnt. Okay, so basically we saw that how to find out the response, the free vibration response of an undamped system. Okay, and basically what we do, we find out the time variation of the generalized coordinate for each mode. Okay, we find out the constants, unknown constant, using the initial conditions, and finally we combine all those modes using the modal coordinate at any time t. Okay, and we can find out the response, total response, as a function of linear combination of all those mode shapes. Okay, so we can do an example of this and then see, okay, demonstrate the free vibration response. So let us again take the same example. Okay, so this is here 2k and k here, this is 2m and m here. Okay, Again, phi1 and phi2 have been given to it. Now, what is given as initial conditions have been given to us. So u0 is basically half and 1. Remember, this is u1 here, and this is the second degree of freedom u2. And the initial velocity is also given as 0, 0. Okay. So let us see what do we get as the overall response. Okay, the ut value. To do that, first I need to find out these factors q1 of t and then q2 of t. Okay, let us see how do we get that. So basically q1 of t would be nothing but phi1 t mass times u0 divided by m1, which let me write it as phi1 t mass phi1 here. Okay, and once we substitute all the values here, so this phi t would be basically half 1, then I have the mass matrix 2m 0 0 m, and then u0, which is basically half 1. Okay, and I again have half 1 2m 0 0 m and half 1. Okay, so we can get this q1t as the this value as, okay, sorry, this is q1 0 here, not t. As the numerator and denominator is same, we get this as 1. Similarly, q2 0 we can get as doing the same thing. Okay, just replace phi1 by phi2. Okay, and this would, you will see that after you substitute this parameter, this comes out to be 0. In addition to that, q1 dot 0 and q2 dot 0 would be equal to 0 because my u dot, the initial velocity or degrees of freedom, are equal to 0. This is equal to 0. So we can go ahead and in our expression we can substitute q1 of t would be basically equal to phi1 times, okay, or let me just first write down q1 at t is equal to q0 cos omega 1 t plus q dot of 0 divided by omega n sine omega 1 t. Okay, this is omega 1, let us see. Okay, this is equal to 0. q0 is 1, so this I'm left with cos omega n t. Okay, q2 of t would be equal to 0 because my q2 of 0 is equal to 0 and q2 dot 0 equal to 0. Okay, so these two, q1 of t and q2 of t, we have obtained as these expressions. So remember, my ut would be nothing but summation n equal to 1 to 2 here phi n times q n t, which is basically phi 1 times q1 of t, phi 2 times q2 of t, which basically second term is equal to 0. So this is I get as half and 1 and times cos omega 1 t. Okay, so this is the response that I get for each degree of freedom, or in combine the ut as 1 by 2 and 1 times cos omega 1 t. Okay, so this was the first part. Let us again find out the response for another case in which, okay, so I'm considering another case, and in this case the initial displacement has been given as minus 1 by 2 and 2. Okay, and u2 dot is actually equal to 0 0. Okay, so we can again follow the same procedure. Okay, and we can write down the displacement as 1 by 2 and 1, or let me, before writing that, remember this is my first degree of freedom, this is the second degree of freedom. Okay, I can write this as phi 1 times q1t and phi 2 times of q2 of t. So this we get as half times 1 times cos omega 1t plus minus 1 and 1, the second mode shape, times cos omega 2t. Okay, so this is the response for the second case. Now the reason that we did like in the two cases, I wanted to show you something. You have a look at the response here and the response here. What can you tell me about these responses? If you look at it, and if you, the response for the first one, this is actually a harmonic motion at each degree of freedom, right? Because it is a cos omega t type, okay, as a cos function. However, in the second one, I have some function times or some vector times cos omega 1t plus another vector times cos omega 2t. So this is not a harmonic variation because I have two frequency and it cannot be written as some constant times some cos or sine variation. Okay, had it been the same angle omega 1 and omega 2 equal to omega, then I could have done that. Okay, but not in this case. So in the first case, the response is harmonic, whereas in the second case, the response is non-harmonic. Okay, one more thing to notice here. In the first case, I can see only the contribution due to the first mode. There is no contribution of the second mode. There is no omega 2t term here. Okay, however, here you can see that there is contribution of both modes. Okay, so only the contribution of first mode in the first case, while in the second case there is contribution of both mode, and that can be explained directly if you look at the initial displacement. Okay, for the first case, remember the initial displacement was half and 1, which is also the first mode shape of the given structure, and by definition, as we have previously discussed, if you assign initial displacement to the structure which is according to the one of the characteristic shape, then it is going to respond harmonically while maintaining its shape, and it is going to vibrate in a particular mode of vibration. So there would be no contribution of any other mode. So that's why we don't see any contribution of other modes, because it is being vibrated with initial displacement which is one of its mode shapes. Compare that to second one, the initial displacement here is not one of its mode shapes. So in general, when we provide initial displacement, we will have contribution of both modes, and the response would not be harmonic at each degree of freedom. Okay, and we have just seen example of that. Okay, whatever we had discussed. Okay, all right. So I hope this example is clear. Now let us get into damped free vibration. Okay, so we have discussed undamped free vibration. Now let us discuss damped free vibration. Now for the damped free vibration, we will now have an additional damping term here with the damping matrix C here. So this is equal to 0. Okay. Now in this case, if you look at it here, I have this damping matrix. Okay. Now the reason I was able to solve the undamped free vibration, because my mass matrix and my damping matrix could be diagonalized. Okay, The solution for damped free vibration would depend on the fact that whether my C matrix can be diagonalized or not. Because if I'm able to diagonalize my C matrix or the damping matrix, then I can uncouple all the equation of motion for all the different modes. So I would have n uncoupled differential equations. Okay, and then I could solve those and combine the responses using the modal expansion vectors. Okay, so whether I can solve this analytically or not, it would depend on C. Okay, so basically C plays a big role. Now, if C is a classical damping matrix, okay, so if C is a classical damping matrix, okay, so let me write it here. C is classical damping matrix if it can be diagonalized. Okay, and how do we diagonalize this? Okay, how do we diagonalize any matrix? We multiply with the modal matrix, okay, and then see whether it can be diagonalized or not. So let us say it becomes C2 Cn as Cn, this is 0 and 0. Okay, and if it can be diagonalized, we call it a classical damping matrix. There are non-classical damping matrices as well, and there are some methods of solution for those as well, but that is not within the scope of this course. Okay, so let us consider classical damping matrix where C can be diagonalized and then see if we can get solution to this damped free vibration. So what we are going to do here, I am going to write my U as the modal matrix times the modal coordinate vector Q here. Okay, of course it's QT, I'm dropping the T term here. Okay, so first I'm going to substitute this, and then I'm also going to pre-multiply with the modal matrix transpose. Okay, so this is the acceleration of the modal coordinate. Here again phi t times C times U dot, which I can write it as Q dot here, and then phi t times K times phi, okay, times Q. Now as we know, this is diagonal mass matrix, this is diagonal damping matrix, and this is diagonal stiffness matrix. So this can be written as mass times the Q vector, okay, the diagonal mass matrix times the modal acceleration vector, and then this as diagonal damping matrix times velocity vector here, and then the diagonal stiffness matrix times the Q vector here. Okay, and because remember all these expressions are in terms of m1, m2 and so on, let us say mn here like this, and then q1, q2 and so on. Similarly c1, cn, okay, q1, q2 plus k1, k2, okay, all these are uncoupled and uncoupled differential equation. Okay, and for the nth mode, okay, for the nth mode I can write it as mn qn plus cn qn dot plus kn qn is equal to 0, which is of the form of the free vibration response of a single degree of freedom system. So I have basically decomposed my multiple degree of freedom system through the modal decomposition into n single degree of freedom system. and then I'm going to find out the response for each system, which would be basically response for each mode in terms of the modal coordinate q and t. And once I have the q and t, we know that we can combine all the modes using the multiplication of the mode shape times the q and t using this expression here. Okay, now like what we did for free vibration response of a damped undamped system, we can do the same thing for the damped system as well. Okay, and q and t can be similarly obtained. Okay, now to do that, let me first do this. Write down the same equation that we have, okay, by dividing throughout by mn and writing it in this form. Okay, qn plus 2 zeta n omega n, okay, times qn and omega n square times qn equal to 0. Okay. Now if you look at here, we have damping for the nth mode. So now for a multi-degree of freedom system, the way the damping ratio is defined, there is a separate damping ratio for each of the mode. Okay, and that damping ratio is nothing but Cn divided by C critical, which is 2 Mn omega n. Okay, and my Q and T can be written as minus zeta omega n times T here, then Qn 0. Now I would have, remember, now there is a damping in each of the modes, so I have to consider the damped frequency. So this is the omega n dt, okay, plus 1 dot 0 zeta n omega n times omega n d times sine omega n. Okay, this is similar to the expression that we had obtained for the damped response of a single degree of freedom system. Only now we are considering everything for a particular mode. So this is the response for the nth mode. Okay, and we have defined the damped frequency for the nth mode as omega n times 1 minus zeta n square. Okay, and the total response I can write using the expression that I had here as ut equal to summation n to n phi n q and t, where q and t is basically this expression here. Okay, so this is how we get the response, the damped response free of a free response of a damped system. Okay, now if we notice in this case, typically we do not get the damping matrix. So I've told you that you can get the damping matrix and see if it can be diagonalized or not. Okay, but in practice there is no way we could get the damping matrix by just considering damper element in a structure. Okay, so what we typically do for practical analysis, we assume or we determine experimentally the damping ratio for each mode, because remember now the damping is defined for each of these modes. Okay, and there are some experimental methods to do that. Okay, or we can assume some values based on the data that we have observed in the past from the testing or the response of other type of structures, similar structures.